Hey guys, so in this video I'm going to be trying to make a Cockcroft Walton generator with which I will have access to huge tens of thousands of volts. So let's get right into the explanation. So the actual reason I'm doing this project and building the Cockcroft Walton generator is because I need some very high voltages for an upcoming project which needs somewhere in between 40 to 60,000 volts unless it just won't work. And so I need to make this voltage myself because buying a power supply that goes that high is very hard and expensive and unrealistic. So I will have to make it myself, and with the Cockcroft Walton generator is how I'm going to do it. So let's get right into the explanation and see how it works. So this is what a schematic of a Cockcroft Walton generator looks like, right? So those right here are two stages. Each stage looks like this and has got two capacitors and two diodes. So right here you have your input. For me, it's a transformer, and usually it is a transformer. Well, to be more precise, it's not a regular transformer that operates with low frequency, for a reason I will get into later. But this is actually a ZVS flyback transformer. How that works, said in a short manner, is it takes some DC voltage input, and then with some MOSFETs, or generally just transistors, it makes a very huge AC frequency. With that very large frequency, you can take some smaller transformer cores to, well, transform it. And with that input, I have 10,000 volts. And so how it works, the circuit, is you have a bunch of capacitors and they are in series. And so the voltage then just adds up, because that's what voltage does. And the diodes are there to prevent the backflow from happening. And so then the voltage in this particular circuit, this would be positive, and this beginning at this point at the beginning would then theoretically be negative. So this is how the voltage ideally behaves when, depending on the number of stages on the Cockcroft Walton. So if you have this sine wave input, the first stage looks like this. It is just that the voltage difference at every point in time is either positive, as I do it right here, or negative. It doesn't really matter too much. And then what happens after the first stage is something slightly different. It's that the voltage shifts up, but only twice as much from the first stage, because every highest voltage from the one stage is the lowest voltage from the stage after that. So if I want to achieve 40 to 60,000 volts with two stages and a 10 kilovolt input, I would get 40 kilovolts peak with two stages, and with three stages I would get 60 kilovolts peak. Now, unfortunately, reality. Oh my god! Now, unfortunately, reality is not that simple. In Cockcroft Walton generators, you have voltage drop given to you by this pretty long formula. It depends on the current, the capacity, the frequency, and the amount of stages. And it depends on the amount of stages pretty heavily, because you can see there's even a cubed term in there. So if you do want to make a higher amount of stages, you either need some very high frequency, or some very high capacity, or some very low current. So how I mitigated the problem of goddammit, right? And how I mitigated the problem of voltage drop is by frequency. You see, the ZVS already has a frequency of around 50,000 hertz, which is plenty enough to bring my voltage drop down to only a few hundred volts, which might sound like a lot, and in regular everyday circumstances it is. However, when dealing with like 40,000 volts, it's really negligible. So with nothing left to say, let's get right into the building process of it. So here is my ZVS. I bought this, and the voltage of 10,000 volts is supposed to be between those 2 points. So let's turn it on and see how it works. Let's do this. I'm gonna move it by here. Hey! What the f***? What the f***? Well, that's confusing. How is there such a big arc between me and the wire? I mean, I get it's because of grounding, but how is there such a good connection that this huge arc forms, and how can I not feel it? I mean, I guess because of the higher frequency, it might feel like less, right? And with the high frequency, it gets less dangerous too, because of something called the skin effect, where in very high frequencies, electromagnetic, or rather just electric forces play together to kind of push the current into the rather surface, I know that word doesn't exist, into the surface of the object that the current is passing through. For example, for humans it would be, well, skin. But what? Let's just try again. So let's just try it again, I guess. And this is so weird. How is it going through me and how am I not feeling a thing? So let's, I guess, ignore the... Okay, this seems to be working. Still some... Oh my god, this is... Oh! Whew, that looks like it's pretty hot. This is sounding very cool. Oh, cinematic. Oh my god, I cannot stop playing around with this. This is so fun. Oh my god, oh my god, oh my god. Oh my god, my hand touched this thing right here. Okay, I guess I got some current through me again. Michael is kind of curling. Oh my god, what the f? Well, it appears I've burned my hand a bit. Happened, I guess. Well, at high, let me just remind you that at high voltages, everything is miserable and everything is a conductor. Look at this. I was, again, stupid as I am, playing around with this very weird phenomenon, and all of a sudden, it all started arcing internally. That's not good. So I did it. I built the Cockcroft Walton, and here it is. It's a piece of shit. I am aware. It's just a few capacitors glued together, and the contacts are, just intertwined. I know it's not a great solution, and I could have done this way better with soldering, because I had the technology to do that. But I do not possess the patience to solder all of this together. And well, because it should be fine without doing it out there. And anyway, those are old diodes. And I made the circuit before and I instantly blew them because the current got overloaded. Those can only handle 5 milliamps. And so, yeah, I had to go buy new ones. Pretty expensive. Anyway, let's see how they work. Okay, the installation is finished. What is the installation? Let's see if it works. I'm pretty excited, so let's turn it on. Oh, that's... Okay, that's pretty loud. Now, okay, one thing you shall not forget. Those are capacitors. And you know what capacitors do? They hold charge. So, if you do not pay attention, this could go through your body. Yeah, wouldn't want that to happen. You know what I just noticed? The contact, or actually rather this wire, gets way closer to the other one if I turn it on. Look at this. I think you can see it now. Yeah, that got closer. Oh, this is so loud. Oh, I have tinnitus, whatever. So let's check out how far that arc will jump. So right here we have around 2 centimeters, pretty much. The problem is I'm not measuring this precisely because you see those contacts right here, they are pretty much in this way, right? So corona discharge could go, wait, let me discharge this. Yep, there still was some charge on that. So corona charge could theoretically go from up there. So the arc right here does not contain 100% of the voltage, I guess. Well, that's not entirely accurate, but whatever. Now let's check it out. So this is 2 centimeters. If it jumps that, how many volts is that? I'm gonna put it right here. They say 1 millimeter of arc equates to roughly 1 kilovolt in, voltage. However, I'm not sure this is entirely accurate, so let's just see how far it'll jump. Oh my, that is so loud. That is inconceivably loud. Actually, now I'm kind of interested too in seeing what would happen if I put a resistor in series, and I have ordered some big ones, 10 mega ohm. That's 10 million ohms. That's pretty much. Because then, if you remember the formula of the voltage drop, right? The current is actually proportional to the amount of voltage drop. So if you put a 1 mega ohm resistor in series, we can see how much voltage drop was actually affecting the voltage, because then basically voltage drop will jump basically to 0. Okay, so when I put the resistor in series right here, right, I put some tape around it so that it doesn't spark around it. Oh, goddamn. You can see, I mean, that's nothing, and it still has trouble discharge. Wait, come on, please spark again. Oh yeah. Oh god damn. Okay, it looks like the resistor has failed. So yeah, I guess that's kind of bad. Looks like 10 mega ohms were a bit way too much. Should have went with the 1 mega ohm, I guess, or like 100 kilo ohm. Okay, so I made a few changes. First off, there's this plastic thingy. It's just because the arc doesn't jump on the table. Not the arc itself, but there has been significant corona discharge if I try to do it on the table with something like this. And I use these things such that I can more accurately control like the distance and make it further apart, right? And yeah, let's check if it does go. Does go this far, but now let's see how far I can go, and then I'm gonna play around with some fire. And by the way, while reviewing some of the footage, I actually noticed how much the audio loudness, I guess, drops, and it does so stupendously much whenever the arc activates, right? Because I mean, it is really so extremely unfathomably loud. Let me demonstrate. Okay, I'm going to be talking something random throughout this arc. Okay, speaking now, and I mean, I think it's starting to recover now, but I mean, this is just crazy. Anyway, let's push this to the limits now and see how far the arc can stretch. Okay, look at this. Oh, I have so much tinnitus. Okay, so let's look at this right here, and this is a gap of around 2.5 centimeters, a bit more. Now let's see if it can stretch that far. Okay, here we go. Yep. Looks like it can. Okay, let's check out this gap. Oh my god, why the fuck did I get a shock from that? What the fuck? Looks like we had roughly 3.5 centimeters right here. Let's keep on going and hope I don't get it shocked now. I mean, I really don't know why. Okay, let's check this out right here. I'm gonna stand far back. Okay. Almost 5 centimeters. So why does this happen? How does fire conduct electricity way better than regular air does? Well, you see, an arc itself is basically just ionized air, right? If you have a high enough voltage such that the air reaches its breakdown voltage, what then happens is the air, well, breaks down and ionizes. And after it's ionized, it's way easier to maintain that arc, since it already is ionized, right? But you see, in fire, it's a bit different than regular air, room temperature air, right? Because fire is already a bit ionized and very hot. And with that heat also comes the ability that electrons can be knocked off and ionized easier. So that's the reason. And basically that's it for this video. Thank you for watching. I hope you liked it.